Hello, I'm Orit, uh, Assistant Professor at Basic Science Department at Gargi Memorial Institute of Technology. In the last lecture of statistical mechanics, we have studied about the what is phase space, what is phase cell. We calculate the number of phase cell per unit volume. So today's lecture we try to consider the we try to find out the density of state. So we are studying from first. So densities of state. What is density of state? For the calculation of the density of state, we need a quantum mechanical concept. So we have already studied or we are already construct a energy equation or energy equation for the three-dimensional box, because when we try to calculate the energy of any particle in a box, suppose in a chamber. So obviously this box have a the box have a three-dimensional geometrical shape. So from the quantum mechanically, the energy eigenvalue in the 3D box with age Lx, Ly and Lz, the dimension of the box Lx, Ly, Lz. So the energy is written in term of h square by 2m nx square by lx square plus ny square by ly square plus nz square by lz square. We have already constructed this equation in a three-dimensional box, potential box problem in a quantum mechanics, where is nx, ny and nz are the integers value. Okay, so this is the energy. Now we try to consider this energy. We converted the energy into a momentum term. Okay, we try to consider this quantum state in term of, because this quantum state are there in term of energy. We just converted this energy state, quantum state, in term of momentum. That's why we have a equation for the energy momentum. Equation is p square by 2me. So obviously p is become root under 2me. So p is equal to root under 2. You just put the value of the e from here to here. H square root under h square by 2m nx square by lx square plus ny square by ly square plus nz square by lz square. So obviously the each component of the px py, if you separated the each component of the momentum px py pz, is written by px is equal to obviously lx nx by ly, for the pz ph ny by ly, and the z component pz is equal to h into nz by lz. Okay, now we consider a momentum sphere. So this is a, suppose this is a pz component, this is a px component, this is a py component. The radius of this sphere is p. If you change the momentum of this sphere from p to dp, suppose the changing of the momentum is dp. So obviously if you change the momentum from p to dp, because suppose this point is p and this point is p plus dp. So changing the momentum from p to dp, the energy, the quantum energy state, or the quantum number is slightly changed. That's why we written here del nx is equal to lx by h in term of dpx. Similarly for the n, del ny is equal to ly h into dpy. This is, and the nz ly, nz equal to ly by h p dz. The small change of dpz, the quantum numbers change is del nz. Now if you change the number of state for which momentum component is changed from the component of px change to px plus dpx, the y py to py plus dpy, and pz to pz plus dpz. Then the total quantum state is become a del nx, del ny, del nz is equal to lx, ly, lz by hq dpx, dpy, dpz. If you consider Lx, Ly, Lz is the volume of the potential box, so we can written here del Nx, del Ny, del Nz is equal to V by H cube dpx, dpy, dpz. Is it clear? So now so this is the okay. So this is the energy, this is the quantum state. Okay. Del nx, del ny, del nz is equal to V by H cube dpx, dpy, dpz. This is the energy state of the changing of volume from P to P plus dp. So in this equation we can see that the every term is separated by each component. If you each component, because this term is responsible for the x, y, z. Okay. For now, change of volume, equation 1, volume 2 concentric sphere of radii p to p plus dp. Okay, so obviously we draw here this. So this is the p and this is the dp. Okay, so this is a sphere, spherical body, because this is a three-dimensional picture. Okay, so the surface area of this sphere is obviously 4 pi p square, and the changing dimension towards the radius is dp. So this equation is considered the volume of this portion, the changing portion, the volume of the changing portion, dp square by dp. Clear? This is the changing volume. So this is the changing volume. So the quantum state is written by Gp dp is equal to V by H cube 4 pi p square dp. How could we get this equation? Okay, this equation 1, this left hand side is a dependent for the changing of quantum state. We just rewrite this whole one in term of function gp, gp. G is a function of p, the changing of state, the constant, the changing of quantum state. Is it clear? And this in the right side, the total, the changing of volume dpx, dpy and dpz we written here in term of p. Here is every component is term of the x, y and z separated by the each component. We just consider this changing volume in term of p. There is no external component. Internally this p is dependent on the x, y and z, but externally the p does not depend on the x, y and z. Similarly, nx, del nx, del ny and del nz, this each changing of the changing of the each component of the state is considered as one function. Okay, this is the quantum state in phase space. Because we considered this dp is changed to 0, the minimum value of dp. So the relation of energy and momentum is p square by 2me. P is equal to obviously 2me and dp is equal to m dE by root under 2m e. Clear? Now we try to convert it this quantum of state equation in term of momentum to energy. That's why we need the value of the p and dp, because we substitute the dp square and dp in term of energy. Okay, now from the equation 2, we have now the function is term of energy dE v by h cube is equal to 4p. Obviously p square is equal to 2me. We put the value p square in term of 2me and the dp is equal to m into dE root under 2m e. Clear? Just ge dE 2 pi by v, because 2 pi by v by h cube 2m whole to the power 3 by 2, because when 2m is the power is added with the m is become 3 and e dE. So ge dE is equal to 4 root 2 by h cube 2m whole to the power, this one is pi m whole to the power 3 by 2 root under e dE. This is the energy. This function, the function ge gives the number of quantum states per energy of range of energy E to E plus D. So from changing of energy from one E to E plus D, the function gives you the number of quantum state. So this is the actually is also known as density of state. Is it clear? This is called the density of state. We have another case is here. This is, suppose this whole thing we are done for the gas particle. So every one molecule contain a one phase cell. Okay, obviously one molecule or one molecule can occupy the one cell, but in the case of the electron is dependent when the electron occupy a energy state. When electron occupy a energy state, so it's depend on its spin, and one energy state is occupied by the two electron for the two different spin. So since an electron has two independent direction of spin, so that's why GE then the density of state GE is equal to 2 into 4 root 2 pi by h cube m to the power 3 by 2 root under e into d. You just multiply the possible quantum density of state is become double, because the occupation of electron in one single state is occupied by the two electron with a different spin. That's why one energy state is occupied by the two electron. That's why the total energy state is become double. 8 root 2 pi by h cube m to the power 3 by 2 e to the power half dE GE dE. This is the energy density of state for the electron, and this is the energy density of state for the any other molecules. Is it clear? So we are done today's lecture, the density of state. In the next lecture we try to separate the molecules with respect to its characteristics. What is that? What we are done in a statistical mechanics, we just try to find out the in the most probable state, in that which state can be occupy the most of the particles or the gas, and what is the energy value at that state, what is the interaction and the behavior of the particle. So what is the in the interaction or the behavior of the particle in the most probable state of any energy value. In this way we divided the statistical pathway, the statistics in a three separate pathway. One is called Maxwell-Boltzmann statistics, Bose-Einstein statistics, Fermi-Dirac statistics. This Maxwell-Boltzmann statistics is also considered as a classical statistics. Why? This statistics is responsible for the gas particle or classical particle. We are study in the Boltzmann statistics we study the Maxwell-Boltzmann statistics, consider the gas particles of the gas particles in terms of molecules or atom. Okay, the Bose-Einstein statistics is also known as quantum statistics. Okay, this statistics is considered for the quantum state particle like photons, phonons or gavons. All is considered as a bosons. Which photons, this type of particle follow the Bose-Einstein statistics. That's why photon and phonon is also named as a boson. Clear? And in a Fermi-Dirac statistics, we consider the half spin particle like electrons, positrons. Clear? And such type of particles is also known as fermions. Is it clear? In the next lecture we try to construct the distribution function we all know that what is distribution function. So in the next lecture we try to evaluate the distribution function for the Max-Boltzmann statistics. Okay, then Bose-Einstein statistics, then Fermi-Dirac statistics. Okay, thank you.